Please subscribe to support the channel. High above the earth, among the glimmering tapestry of night, there is a star that behaves unlike almost any other. A celestial body that seems to have a heartbeat. Its glow waxes and wanes, brightens and fades, as if breathing in rhythm with the cosmos itself. This ancient, pulsing light belongs to a star named Mira, a name that means the wonderful. It is a title well earned, for few stars in the universe tell a story as dramatic, mysterious, and enduring as this one. Mira has often been called the star that refuses to die. In a universe where most stars burn steadily until they quietly fade, Mira stands apart, a dying star that continues to blaze defiantly against the dark. Every few hundred days, it dims so much that it disappears from the naked eye, only to re-emerge months later, bright and beautiful, as though resurrected. To early astronomers who believed the heavens were fixed and unchanging, Mira was nothing short of a cosmic miracle, a star that shattered the illusion of permanence. It's easy to imagine the awe of those first skywatchers who noticed Mira's vanishing act centuries ago. One year, a bright point of light gleamed in the constellation Cetus. The next, it was gone. And then suddenly, it returned again. What could explain such a phenomenon? Modern science has revealed the truth. Mira is an ancient red giant, nearing the end of its life, and it is literally pulsating, expanding and contracting in a cosmic rhythm as it struggles to maintain equilibrium. But beyond the science lies something deeper, almost poetic. Mira's fluctuating brilliance tells a story of struggle, resilience, and rebirth. It's a reminder that even in death, there can be beauty. Even in decay, there is transformation. For billions of years, Mira burned quietly like our own sun. But now, in its twilight, it performs one of the most spectacular finales in the cosmos. Its outer layers swell and collapse. Gas and dust spill into space, and each time it seems ready to fade forever, it returns, glowing once more as if to say, "I am not finished yet." Astronomers who study Mira often describe it not merely as an object, but as an event, a living process unfolding before our eyes. Its light takes 300 years to reach us, meaning that every flicker we see is a message sent centuries ago from a star nearing the end of its life. And yet, even after all this time, Mira continues to burn, to breathe, and to defy oblivion. There is something profoundly human in that. We too are made of the same stardust Mira releases into the cosmos. We too fight against time, burning brightly before fading into memory. Perhaps that is why Mira captivates not only astronomers, but dreamers. Because in its flickering, dying light, we see a reflection of our own fleeting brilliance. In the grand silence of the universe, Mira stands as a beacon of persistence, a star that will not surrender quietly to the darkness. It is a cosmic heartbeat, echoing through the ages, whispering that even in the universe's inevitable decay, wonder never truly dies. Mira, or as astronomers formally call it, Omicron Ceti, is a star that drifts in the quiet depths of the constellation Cetus, the celestial whale. It lies roughly 300 light-years from Earth, close enough for its light to reach us after a journey of only 3 centuries. A blink of an eye in cosmic time, though to human history it's the span of empires rising and falling. Through the darkness of space, that light carries a story billions of years old, one written in the slow-burning heart of a dying star that has seen the galaxy change around it. When we look towards Cetus on a clear night, we peer into a region of the sky that ancient civilizations once saw as part of the great sea that flowed beneath the heavens, a place populated by mythical creatures like the whale, the fish, and the river. Nestled within that quiet patch of sky is Mira, A star that doesn't stay still, not in brightness, not in nature, not in temperament. Mira is a red giant, which means it is a star that has reached the end of its main sequence life, the long, stable phase that stars like our Sun occupy for billions of years. During that earlier era, Mira burned hydrogen in its core, fusing atoms together to create helium, and in the process, releasing the energy that sustained its brilliance. But now, Mira's hydrogen is almost gone. The delicate balance that kept it stable for eons is breaking down. As the internal nuclear fires fade, gravity begins to pull inward while the outer layers push outward, struggling to find equilibrium. The result is a star that has expanded to a size hundreds of times larger than it once was. If we could place Mira where our Sun is, it would stretch far beyond Mercury and Venus, possibly reaching Earth's orbit. And yet, despite its enormous size, Mira's outer layers are tenuous, almost ghostly. Vast clouds of glowing gas that shift and move as the star breathes in and out. In astronomical terms, Mira is classified as a pulsating variable star, one of the first ever known. Its temperature hovers around 3,000 degrees Kelvin, much cooler than the Sun's 5,800 K, which gives it that deep ruby red hue that astronomers see when they capture its light through a telescope. But its luminosity, however, fluctuates enormously. When Mira is at its brightest, it can shine nearly 1,000 times more luminous than our Sun. But when it dims, it fades to a fraction of that brightness, sometimes becoming invisible to the naked eye.
To understand what makes Mira so special, one must appreciate where it sits in the grand timeline of stellar evolution. Stars like Mira start their lives as massive clouds of hydrogen gas. Under gravity's pull, they condense, ignite, and shine steadily for billions of years. But when the core's hydrogen runs out, the balance between pressure and gravity collapses. The star's core contracts, heating up, while the outer layers expand outward. This expansion cools the surface, turning the star red, the signature of a red giant. Mira is in this very phase, a luminous but unstable relic of its former self. If you could see Mira up close, you'd witness an almost alien sight. Its surface wouldn't be smooth and golden like our Sun's, it would be a churning ocean of convective bubbles, each one larger than the distance between the Earth and the Moon. Great plumes of gas rise and fall, glowing with a faint red light, while shock waves ripple through its atmosphere. Every few hundred days, these shock waves cause the entire star to expand and contract, pushing its brightness to dazzling peaks before letting it sink into near darkness. This is what makes Mira so mesmerizing to astronomers. It's not a static object, but a dynamic, living system, one that embodies the constant tension between creation and destruction that defines the universe. Its variability is not chaos, but rhythm, a cosmic heartbeat. And there's another layer of intrigue. Mira is not alone. Though it appears as a single point of light to the naked eye, it is actually part of a binary system. Two stars locked in a slow gravitational dance. The main star, Mira A, is the famous red giant whose brightness ebbs and flows. Its companion, Mira B, is a small, dense white dwarf, the remnant core of a long-dead star. The two orbit each other at a distance roughly equal to that between our Sun and Neptune, exchanging material and shaping each other's fates. Over time, gas from Mira A's extended atmosphere is drawn toward Mira B, forming streams of matter that spiral around the white dwarf like a ghostly ribbon. This strange companionship adds to Mira's mystery. From our perspective, it is a symbol of duality, life and death entwined. Mira A, though dying, still gives, shedding its outer layers into space. Mira B, though long dead, still consumes, feeding on the remnants of its partner's fading light. Together, they tell a story that is both tragic and beautiful, a stellar partnership that has lasted for millions of years. When we speak of Mira being about 300 light-years away, it's easy to underestimate just what that means. The light that reaches our eyes tonight left the star around the year 1725, when humans were sailing wooden ships and writing by candlelight. In all that time, while our world changed beyond recognition, Mira continued its endless cycle of dimming and brightening, an ancient rhythm indifferent to the tides of human history. In the grand scheme of things, Mira is nearing the end of its existence, yet its very instability ensures that it remains vibrant and risible. It is shedding its mass into the cosmos, atom by atom. And those atoms, carbon, oxygen, nitrogen, will one day become part of something new. Perhaps a nebula, perhaps another star, perhaps even a world where life takes hold. Mira is, in every sense, a bridge between what was and what will be. So, when you look towards Cetus and think of Mira, remember that you are not simply looking at a star. You are witnessing the legacy of an ancient sun, one that has lived far longer than humanity itself, one that now spends its final centuries creating the ingredients for future creation. Mira is not just a red giant in the sky, it is a monument to the universe's endless cycle of birth, death, and renewal. It reminds us that even as things fade, they give life to new beginnings. It is a cosmic paradox, both ephemeral and eternal, fragile yet enduring. The story of Mira's discovery begins at a time when the universe, to human understanding, was still perfect, unchanging. The year was 1596, a time when the telescope had not yet transformed astronomy, and the stars were still believed to be eternal fires fixed upon the celestial sphere. The very notion that a star could change, could live or die, was heresy against centuries of philosophical certainty. And yet it was in this age of rigid belief that a quiet but sharp-eyed German pastor named David Fabricius made an observation that would forever alter humanity's understanding of the cosmos. Fabricius was not a famous scientist by the standards of his day. He lived in East Friesland, a modest region near the North Sea, far from the grand observatories of Italy or Prague. His life was simple, his occupation humble. He served as a clergyman in the Lutheran Church. Yet Fabricius was a man of curiosity, one who looked not only toward his congregation, but also toward the heavens. In the late 16th century, astronomy was a passion among educated clergy, often seen as a way to glorify the Creator by studying his works. Fabricius had access to the most advanced star charts of his time, and he kept careful notes of his nightly observations. One spring evening in August 1596, while studying the constellation Cetus, he noticed something odd. There was a star visible near the neck of the whale, one that did not appear on any of the star maps he knew so well. It was faint, but unmistakably there. Fabricius recorded it carefully, believing perhaps that it was a new celestial phenomenon, possibly a nova, the new stars that occasionally flared up in the sky. Only a few decades ago, in 1572, the great Danish astronomer Tycho Brahe had made his name by studying such an event, a bright new star in Cassiopeia that had astonished all of Europe. Encouraged by this precedent, Fabricius kept an eye on the mysterious light. But weeks later, to his astonishment, the star began to fade. By October, it had vanished completely, swallowed by the dark. He must have stared at that patch of sky in disbelief. A star that appeared and disappeared at will was something no astronomer had ever documented before. The heavens were supposed to be immutable. A star that changed its brightness so dramatically contradicted every philosophical doctrine handed down from Aristotle to Ptolemy.
Fabricius wrote of his discovery cautiously. He described the star as Omicron Ceti, a new star in the neck of the whale. He could not have known it at the time, but he had just documented the first known variable star, the first celestial object observed to change in brightness periodically. His finding marked the beginning of a new chapter in astronomy, the realization that the universe was dynamic, restless, and alive. Curiously, after Fabricius's initial sighting, the star remained invisible
for more than a decade. Many who read his notes dismissed the event as a transient nova, perhaps even an observational mistake. It was not until 1609, 13 years later, that the star returned to visible brightness, reappearing in the same position. By then, Fabricius had passed away, never realizing that his humble observation had unlocked one of the great mysteries of the cosmos. But others had taken notice. The reappearance caught the attention of several prominent astronomers of the 17th century, including Johannes Hevelius and Ismail Buliau, who later confirmed its periodic behavior. But in that moment of 1596, when Fabricius first noted its strange disappearance, the world was not ready to understand what he had seen. The scientific language to explain stellar variability did not yet exist. The idea that a star could pulse, that it could physically expand and contract, was centuries away from discovery. And yet, in hindsight, we can see how monumental Fabricius's observation truly was. Before Mira, humanity thought of the stars as eternal, each a perfect, unchanging point of light fixed since the creation of the world. After Mira, that illusion began to crumble. The cosmos, it turned out, was not static, but dynamic. It could evolve, flicker, and transform, just as the Earth and its inhabitants did. Fabricius's discovery cracked open a door through which later astronomers would peer and find a universe far more alive than anyone had imagined. It's worth pausing to reflect on the courage it must have taken to announce such a discovery in the 16th century. The very idea that the heavens changed was controversial, to many even blasphemous. Tycho Brahe had already faced criticism for challenging Aristotelian cosmology with his Nova of 1572. Fabricius, a pastor bound by the theological thinking of his time, must have felt the weight of that tension. Yet he trusted what he saw. He believed his eyes and his instrument over dogma. A quiet act of scientific bravery that went largely unrecognized during his life. Today, when astronomers chart thousands of variable stars across the galaxy, they owe a debt to that single moment in 1596 when a village pastor dared to believe that the night sky was not eternal. That one observation marked the dawn of variable star astronomy, a field that would later reveal pulsating giants, eclipsing binaries, and even the rhythmic flickers of distant exoplanetary systems. Fabricius did not know he had found the variable star. That term didn't even exist yet. But he had noticed something fundamental. The light of Mira was alive, not constant. It breathed. It changed. And that discovery reshaped our view of the universe forever. In the centuries that followed, other astronomers would track Mira's changes meticulously, confirming that its light followed a 332-day cycle, waxing and waning with clock-like precision. But at its root, all of that modern understanding began with one man, a patient observer who looked up at Cetus and saw something the rest of the world had missed. The night Fabricius first watched Mira faint from view, he might have felt confusion, even disappointment, not realizing that he had just glimpsed one of the universe's most profound truths, that nothing, not even the stars, lasts forever. Yet in that fading light, he had unknowingly uncovered a form of immortality. For as long as astronomy endures, the name of David Fabricius will be forever linked to the first heartbeat we ever heard in the heavens. When the 17th century dawned, Europe was entering a new age of scientific wonder. The telescope had just been invented, Galileo was beginning to revolutionize humanity's understanding of the heavens, and the slow unraveling of the old, rigid celestial order was well underway. It was during this period of transformation that Johannes Hevelius, a brilliant astronomer from the city of Danzig, now Gdansk, Poland, turned his attention to the mysterious, flickering star that David Fabricius had recorded decades earlier. The strange light in the constellation Cetus that seemed to vanish and reappear as if governed by some celestial rhythm. Hevelius was not only a meticulous observer, but also a man deeply enchanted by the poetry of the heavens. To him, the universe was a living work of art, and each celestial body told a story. When he observed this peculiar star, sometimes bright, sometimes invisible, he saw in it something truly extraordinary, something that defied both reason and expectation. No other known star behaved like it. This wasn't a comet streaking briefly across the sky,
nor a nova flaring into existence and then fading forever. This was a star that returned, a light that died and was reborn again and again. By the mid-1600s, Hevelius had studied the star's behavior closely, and in 1662 he published his findings in his monumental catalogue of stars, Historiola Mirae Stellae, describing its incredible variability. Moved by its uncanny and wondrous nature, he bestowed upon it the name Mira, derived from the Latin mirabilis, meaning wonderful, astonishing, or miraculous. It was a name chosen with deliberate reverence, for Hevelius was keenly aware that this star was something new under the heavens, a phenomenon that captured both the beauty and mystery of the cosmos. To name a star Mira in the 17th century was no small gesture. The very act of naming held symbolic weight. It was a declaration of discovery, a way of fixing a celestial mystery within the language of human awe. In giving it this name, Hevelius wasn't just labeling an astronomical object, he was honoring its character, the way it seemed to challenge the assumption that the heavens were immutable. To Hevelius and his contemporaries, Mira was a revelation, a contradiction to Aristotle's claim that the stars were eternal and unchanging. Here was a star that defied the eternal, a cosmic rebel in a sky once thought to be flawless and still. Hevelius was known for his painstaking precision. His instruments were handcrafted, his charts drawn with such care that they remained some of the most accurate of his era. Night after night, he charted Mira's fluctuations. He saw it vanish below the threshold of visibility, then climb again to brightness visible even to the unaided eye. He must have felt an almost emotional connection to it, the way a naturalist might to a creature that appears elusive, retreating into shadow only to return, radiant and alive. The more Hevelius studied Mira, the more he came to understand that its brilliance wasn't random, but cyclical. He could not yet explain why the star changed, for the physics of stellar pulsation were still centuries away from discovery, but he could see the pattern clearly. Mira was not a transient phenomenon. It was a living, breathing object, a star that followed its own internal rhythm, its own heartbeat. It is easy to imagine Hevelius standing in his observatory in Danzig, a place filled with telescopes of his own design, vast sextants and celestial globes, gazing out through the frosty night air toward the constellation Cetus. The sky above him would have been silent and eternal, yet one point of light would stand apart, Mira, winking faintly, as though aware of his gaze. Hevelius, a man of both science and wonder, would have understood instinctively that this star deserved a name worthy of its nature, and so he called it Mira, the Wonderful. In doing so, Hevelius captured the essence of what this star represented, not only scientifically, but philosophically. Mira became more than just a designation. It became a symbol of astonishment, a reminder that even in an age of reason and measurement, the universe still held mysteries that could move the soul. For early astronomers, this was something almost sacred, the idea that the heavens could surprise them, that even the most familiar constellations could harbor secrets yet to be revealed. Hevelius's choice of name also reflects the spirit of his time. The 17th century was a period of awakening, when the walls separating science, philosophy, and faith were still porous. And so Mira's name endured. Long after Hevelius's death in 1687, the title he gave it remained, echoing through centuries of astronomical research. Even as our understanding deepened, as we came to know that Mira's pulsations were caused by the expansion and contraction of its outer layers,
driven by the unstable fusion processes within, the name Mira still fit perfectly, for no matter how much we learned, the star remained astonishing. It's telling that few other stars have been named with such affection and wonder. Many carry cold designations, catalog numbers, or Greek letters, marking their order within constellations. But Mira's name carries emotion. It reflects the sense of awe that even the most rational minds felt upon witnessing its strange behavior. To this day, when astronomers speak of Mira, they are invoking a word that blends science with wonder, a legacy that stretches back to the age when men first dared to believe that the heavens were not fixed, but alive.
Mira's name, given more than 3.5 centuries ago, continues to resonate because it captures the essence of discovery itself. It reminds us that even the most ancient lights can surprise us, that even the most studied skies can still astonish. Every time Mira fades and reappears, it reaffirms Hevelius's choice. It remains miraculous, wonderful, unendingly so. And in that sense, Johannes Hevelius didn't just name a star, he named an idea. He gave language to a truth that would echo through generations of astronomers. That the universe, and all its vastness, is not a clockwork machine of perfection, but a living symphony of change. Mira, the wonderful, stands as both proof and symbol of that revelation, a single pulsing reminder in the dark that even the oldest stars can still inspire astonishment. When astronomers first began to grasp that the heavens were not immutable, that stars like Mira could change their brightness over time, it was as though a curtain had been drawn back on a hidden dimension of the cosmos. The fixed stars, those steady, eternal lights by which ancient sailors steered their ships and astrologers drew their charts, were suddenly revealed to be anything but fixed. They pulsed, flickered, and dimmed. They swelled with power and then faded into ghostly faintness. Some even vanished entirely, only to reappear as if resurrected. This realization marked one of the great paradigm shifts in the history of astronomy, the birth of the study of variable stars. A variable star is, quite simply, a star whose brightness, its apparent magnitude, changes when observed over time. At first glance, this might sound like a trivial matter, but it's one of the most profound discoveries humanity ever made about the universe. For centuries, it was assumed that the brightness of a star was an inherent, unchanging trait. But as instruments improved and observations grew more systematic, astronomers found that many stars defied this rule. Some changed subtly, their brightness varying by only a few percent. Others, like Mira, transformed so dramatically that they could seem to disappear from the heavens entirely before returning in a blaze of light. Mira's behavior was so distinctive and so pronounced that it became the prototype, the archetype, for an entire category of such stars, now known as Mira variables. These are pulsating red giant stars at the very end of their evolutionary journey, characterized by periodic changes in brightness that can span anywhere from 80 to over 1,000 days. The changes are not random. They follow a steady rhythm, a cosmic heartbeat that repeats with almost clock-like precision. Mira's own cycle lasts about 332 days, during which its brightness can vary by more than 6 magnitudes, an enormous range, equivalent to a 100-fold difference in light output as seen from Earth. For astronomers, variable stars like Mira opened an entirely new window into stellar physics. The change in brightness was not due to any external factor, not eclipses, not orbiting clouds, not chance alignment, but rather due to changes within the star itself. Mira wasn't flickering because something was passing in front of it. It was pulsating because its very structure was unstable. Deep within its core, fusion reactions were no longer smooth and steady. Instead, they fluctuated as the star burned the last reserves of its fuel, sending waves of pressure outward through its vast gaseous envelope. These waves caused the outer layers to expand and contract, cooling and heating as they did so,
and with each cycle, Mira's brilliance rose and fell. It is hard to overstate just how revolutionary this concept was. When Mira was first observed, no one could imagine that stars could be dynamic, evolving systems. Yet as more variable stars were discovered in the centuries that followed, including Cepheids, RR Lyrae stars, and long-period variables, astronomers began to realize that variability was not an anomaly, but a natural stage in stellar evolution. It was in fact a sign of life, the pulse of a star approaching death. Mira's name became not only the name of a single star, but of a class, the Mira-type variables. They share several key characteristics. They are red giants, typically of spectral class M, S, or C. They have long periods of pulsation, often several hundred days, and they exhibit large amplitude variations in brightness, sometimes by factors of thousands. These stars are found scattered throughout our galaxy, each one a glowing ember in the vast stellar graveyard that surrounds us. The phenomenon of variable stars proved to be a cornerstone of astrophysics, offering clues about the inner workings of stellar interiors. By studying the way a star's brightness changes, astronomers could infer details about its size, density, temperature, and even the composition of its outer layers. Variability became a diagnostic tool, a way to read the hidden language of stars.
In the centuries after Mira's discovery, astronomers such as Friedrich Argelander and Henrietta Swan-Leavitt expanded the study of variable stars into one of the most powerful branches of observational astronomy. Leavitt's work with Cepheid variables, for instance, revealed that the period of a star's pulsation was directly related to its intrinsic luminosity, a discovery that allowed scientists to measure the distances to faraway galaxies. And yet, all of that knowledge, all of that cosmic cartography, traces back to Mira, the first star that taught humanity that the heavens breathe. There is a kind of poetry in the realization that what seems like instability is in fact a form of rhythm, a cosmic regularity that mirrors the cycles of life and death in nature. Mira's light rises and falls, not randomly but predictably, as though following some ancient pattern written into the fabric of its being. For astronomers, these patterns are not merely beautiful, they are meaningful. They allow us to understand not only how stars live, but how they die, and in dying, how they give back to the universe that made them. Mira's role as the first known variable star also transformed the very way astronomers approach the sky. Observation became not a single act, but a continuous process. It was no longer enough to map the heavens once and declare it done. Now, the sky had to be watched over time, its changes recorded and studied. This new temporal awareness, the idea that the universe evolves not just in space, but in time, was revolutionary. It laid the groundwork for everything from modern astrophysics to cosmology itself. Even now, centuries later, when astronomers point their instruments toward Mira and record its pulsations with precise photometric equipment, they are participating in a tradition that began with the naked eye and the curiosity of a village pastor. The tools have changed, but the wonder remains the same. We watch Mira grow and fade, just as Hevelius and Fabricius did, and we are reminded that the stars are not eternal ornaments of the sky, but living, changing beings, each one with its own heartbeat, its own story. In the grand family of variable stars, Mira stands as the matriarch, the first to reveal her secret, the first to show that the light of the heavens is not constant, but alive. The name Mira Variable honors her not just as a star, but as a revelation, a symbol of the universe's restless creativity. And every time her light brightens across the cold night of Cetus, she whispers again the same truth that dawned on those early astronomers 4 centuries ago, that even the oldest stars still have stories to tell if only we have the patience to watch them change. Among all the wonders that Mira presents to astronomers, perhaps the most hypnotic is its pulsation cycle, a rhythmic breathing of light that takes place over the course of roughly 332 days. It is this steady rise and fall in brightness, so regular and yet so dramatic, that makes Mira one of the most remarkable stars in the night sky. Like the heartbeat of a giant cosmic organism, this cycle repeats endlessly, marking the passage of time not in hours or days, but in vast celestial seasons. During each cycle, Mira undergoes an astonishing transformation. When it is at its faintest, it shines at about magnitude 9 or 10, far too dim to be seen with the naked eye and visible only through a modest telescope. But as the months pass, Mira begins to brighten, slowly at first, then more rapidly, as if drawing in a deep cosmic breath. By the time it reaches its maximum brightness, it can shine at magnitude 2, rivaling the brilliance of some of the brightest stars in its constellation and becoming clearly visible even from urban skies. This is a change in brightness by a factor of more than 1,000, a staggering range for a single star. For early observers, this transformation must have seemed like a miracle, hence the star's name, Mira, the Wonderful. They would watch as a dim, almost forgotten speck suddenly came alive, blazing in the neck of Cetus for a few months, before gradually fading back into obscurity. To them, it was as though the heavens themselves were performing a slow and majestic dance, a dance of death and rebirth that repeated with unwavering patience.
Modern astronomy now understands this phenomenon in exquisite detail. Mira's cycle is driven by complex processes taking place deep within its interior. As a red giant nearing the end of its life, Mira's energy production is unstable. The core of the star has exhausted its supply of hydrogen, the primary fuel that sustains most stars, and is now fusing helium into carbon and oxygen. Surrounding this core is a shell where hydrogen continues to burn irregularly, creating surges of energy that ripple outward through the star's vast gaseous envelope. These surges cause the star to expand and contract, alternately swelling to enormous size and then collapsing inward. When Mira expands, its surface area increases dramatically, but its temperature drops, making it cooler and redder. As a result, its overall brightness, paradoxically, decreases, because the energy is spread over a larger, cooler surface. Then, as gravity pulls the outer layers back inward, the gas compresses, heats up, and the star glows brighter once more. This cycle of expansion and contraction is what gives Mira its pulsating light, a regular rhythm born from the star's own struggle for stability. But Mira's pulsations are not perfectly smooth or identical from one cycle to the next. Like the beat of a living heart, there are subtle variations. Some cycles are brighter than others, and the timing can fluctuate slightly, influenced by changes in the star's internal structure and the dynamics of its outer atmosphere. This natural irregularity is one of the reasons astronomers find Mira so fascinating. It is predictable enough to be measured, but chaotic enough to remind us that even stars, in their vastness, have their own quirks and imperfections. The 332-day cycle has been carefully observed for more than 4 centuries, making Mira one of the most thoroughly studied variable stars in history. Generations of astronomers, both professional and amateur, have tracked its changing brightness, plotting its rise and fall in countless light curves that span entire human lifetimes. These records form one of the longest continuous datasets in astronomy, a living chronicle of a star's slow, rhythmic decline toward death. For the casual observer, Mira's transformation is an invitation to witness change on a cosmic scale. When it is near its minimum brightness, you would need a telescope to find it. A faint, reddish ember, barely glimmering in the darkness of Cetus. Yet, as the months pass, the star brightens noticeably. Around the time of maximum light, usually occurring once every 11 months or so, it becomes easily visible to the naked eye. On those rare, clear nights, one can look up and see what appears to be a new star. But it is not new at all. It is the same ancient giant,
returned once more from near invisibility. The beauty of Mira's 332-day cycle lies not only in its physical cause, but in what it represents. This pulsation is the visible signature of the star's internal struggle, a battle between gravity and radiation, contraction and expansion, life and death. The same physical processes that make Mira flicker are also the mechanisms by which it sheds its outer layers into space. With every pulse, Mira loses a little more of itself, exhaling gas and dust that drift outward to join the interstellar medium. Over thousands of years, this gentle shedding will eventually strip the star bare, leaving behind only a white dwarf, a faint, dense ember that will slowly cool for eternity. To an astronomer's eye, each pulse of Mira's light is a message from across time, a record of the energy flows, chemical reactions, and gravitational forces playing out within a dying star. To a poet's heart, it is something more, a heartbeat in the night, a reminder that even the grandest and oldest beings in the cosmos move in cycles, breathing light and shadow just as we breathe air.
What makes Mira's cycle so profound is that it allows us to see time itself at work. Most cosmic processes occur on scales far too vast for humans to perceive directly. The slow formation of stars, the drift of galaxies, the cooling of worlds. But Mira's 332-day rhythm compresses the grandeur of stellar evolution into a timescale that we can watch unfold. In the span of a single year, we can witness a full cycle of brightness and decay, a miniature performance of the life and death that defines all stars. The first astronomers who recorded this cycle could not have known the physics behind it. To them, it was simply a wonder, an inexplicable miracle of light. Today, with our knowledge of stellar interiors, we understand the mechanisms, the equations, the nuclear processes that drive it. And yet, even with all that knowledge, Mira remains just as captivating. Knowing how the dance works does not make it any less beautiful. Each time Mira brightens, astronomers around the world turn their telescopes toward it, recording its magnitude, its color, and its spectral changes. Even amateur stargazers contribute valuable data, continuing a tradition that began with David Fabricius more than 400 years ago. Together, these observations weave a continuous story, a story of a star that refuses to fade quietly, that insists on marking each year with a luminous exhalation before sinking again into silence. So as Mira completes each 332-day cycle, swelling, shining, dimming, and brightening again, it acts as a clock not only for astronomers, but for the universe itself. It reminds us that time in the cosmos is not measured only by orbits and rotations, but by the beating of stellar hearts. Mira's rhythm, steady through centuries, connects us to something eternal, the pulse of the stars, the slow breathing of the universe. The spectacle of Mira's rhythmic brightening and fading, its celestial breathing over those 332 days, is not mere illusion. Beneath its shimmering surface, complex physics are unfolding, driven by the star's struggle to maintain balance in the final, unstable stages of its life. The changing brightness we see from Earth is the outward symptom of deep convulsive processes within Mira's interior, a dance between gravity, pressure, and the restless fires of nuclear fusion. To understand why Mira pulses, one must begin at the heart of the star. Billions of years ago, Mira was much like our Sun, a stable, middle-aged, main-sequence star quietly fusing hydrogen into helium in its core. For most of a star's life, there exists a perfect equilibrium. The outward push of radiation pressure from fusion counterbalances the inward pull of gravity. This delicate balance keeps the star steady, its brightness constant, its shape nearly unchanging. But eventually, the hydrogen fuel in the core is exhausted, and the balance begins to falter. When that moment came for Mira, its story changed forever. Without hydrogen fusion to support it, the star's core began to contract under the immense force of gravity. As it compressed, the temperature and pressure at its center increased dramatically, enough to ignite helium fusion, transforming helium into carbon and oxygen. Around this newly burning core, the star's remaining hydrogen continued to fuse in a thin shell, releasing bursts of energy that forced Mira's outer layers to swell outward. The once compact star ballooned to hundreds of times its original size, becoming a red giant, vast, cool, and unstable. It is within this swollen outer envelope that Mira's famous pulsations are born. The star's immense size and low surface gravity make it exquisitely sensitive to disturbances. Small changes in temperature or pressure can cause its outer layers to expand or contract dramatically. These oscillations, technically known as radial pulsations, occur because the gas that makes up Mira's atmosphere behaves like a spring. When compressed, it heats up and pushes outward. When it expands, it cools and collapses inward. The driving force behind this process is known in astrophysics as the kappa mechanism. It operates through subtle variations in the star's opacity, the degree to which its outer layers block or transmit radiation. In Mira's case, much of its outer atmosphere consists of hydrogen and molecules such as titanium oxide. When the temperature and pressure rise during the compression phase, more of this gas becomes ionized, meaning its electrons are stripped away. Ionized gas is more opaque, trapping heat within the star's outer layers. As the trapped energy builds up, pressure increases until it pushes the outer layers outward, causing the star to expand. But as the atmosphere expands, it cools and becomes less ionized, reducing its opacity. Suddenly, radiation can escape more easily, pressure drops, and gravity pulls the gas back inward. This inward collapse reheats the star, increasing ionization again, and the cycle repeats. It is a natural, self-sustaining oscillation, a kind of cosmic engine driven by light itself. Each cycle of expansion and contraction produces a corresponding change in brightness. When the star's surface contracts, it grows hotter and more luminous, radiating more energy into space. When it expands, it cools and dims, its light softening to a deep crimson glow. These changes are so large that they can be seen from hundreds of light years away, giving rise to Mira's dramatic variation from magnitude 10 to magnitude 2 over the course of its 332-day cycle. Inside Mira, the scale of these movements is staggering. During each pulse, its radius can change by as much as 20%, meaning that its surface moves in and out by tens of millions of kilometers, distances greater than the orbit of Mercury. The energy released and absorbed during each oscillation is immense, enough to light 1 million Earths. And yet despite this violence, the process is remarkably regular, maintained by the precise interplay between radiation, gravity, and thermal expansion. As Mira continues to age, these pulsations are becoming more chaotic and pronounced. Each oscillation sheds a little more of the star's mass into space. Vast plumes of gas and dust that drift outward, forming a thin, expanding shell. Over tens of thousands of years, the stellar wind will carry away a significant fraction of Mira's outer layers. In essence, the star is blowing itself apart in slow motion, its own light acting as the engine of its disintegration. The brightness variations we see are thus both beautiful and tragic, the visible expression of a star's dying breaths. Every pulse is a release of energy, a gasp for equilibrium that can never quite be maintained. Mira's brilliance is not the sign of renewed vitality, but of decay, the unstable burning of fuel in an aging furnace. It is living through what astronomers call the asymptotic giant branch phase, one of the final evolutionary stages before a medium-sized star casts off its envelope entirely and becomes a white dwarf surrounded by a planetary nebula. In a very real sense, Mira is not only shining, it is unraveling. Its outer layers are convulsing, rippling with shock waves generated by the pulsations. These waves heat the surrounding gas, accelerating it outward into space. As the star expands, molecules form in its cooler outer atmosphere, compounds of carbon, oxygen, silicon, and metals, which then condense into fine dust grains. Each pulse contributes to this slow, rhythmic outflow, feeding the interstellar medium with the raw materials for future generations of stars and planets. It's easy to think of Mira's pulsations as catastrophic, as signs of collapse and instability, but they are also profoundly creative. The same physics that destabilize the star also enable it to enrich the cosmos with heavy elements forged in its core. Without stars like Mira, the universe would be a far poorer place. The carbon in our cells, the oxygen we breathe, the calcium in our bones,
All of it was made in ancient red giants like Mira, then scattered into space by pulsating winds just like the ones now flowing from the star. From Earth, these enormous internal processes manifest simply as the slow dimming and brightening of a reddish star in the constellation Cetus. But behind that subtle flicker lies a titanic story of nuclear fire and gravitational struggle, a star at war with itself, fighting against its inevitable end through cycles of breath and release. Mira's variability is therefore not random nor mystical, but the logical outcome of physics playing out over cosmic timescales. Yet knowing that does not make it less wondrous. Every time the star's light rises towards its peak, it is as if the universe itself is inhaling, gathering its energy for another act of creation. And every time it fades, it reminds us that even the most brilliant things in existence are bound to change, to yield, to return their essence to the darkness from which they came. This is the physics of Mira's pulse, the heartbeat of a dying star, driven by the same fundamental laws that govern everything from atoms to galaxies. It is the soundless rhythm of energy and gravity and motion, a pattern so ancient and universal that it echoes, in its own way, the beating of our own hearts. Mira's pulsations and rhythmic brilliance are intimately tied to its current stage of life, the red giant phase, a phase that marks both the zenith and the beginning of a decline of a medium-sized star's life. To understand what this means, it is important to grasp the enormous transformation that occurs when a star exhausts the hydrogen fuel that sustained it for billions of years. Stars, like living organisms, pass through life stages, and the red giant phase is the twilight of that stellar existence, grand, dramatic, and transformative. For most of its life, Mira resembled a typical main sequence star, fusing hydrogen into helium in its core with steady and predictable energy output. That steady burning provided the pressure necessary to counteract the inward pull of gravity, keeping the star stable for billions of years. But as the hydrogen in Mira's core was depleted, the delicate balance between pressure and gravity began to falter. The core, now deprived of its main fuel, contracted under gravity, heating up to incredible temperatures, while the outer layers of the star expanded enormously in response. The star's surface cooled as it expanded, giving it a characteristic deep red hue, the signature color of red giants. In Mira's case, this expansion is breathtaking in scale. Its radius has grown to hundreds of times that of the Sun, making it one of the largest visible stars in our sky when measured by diameter. Its surface area has increased so dramatically that even though its surface temperature has decreased, the total luminosity, the total energy it emits, remains enormous. In this bloated state, Mira is both physically and chemically unstable. Its enormous outer layers are tenuous and loosely bound by gravity, making them easily influenced by the star's internal pressures and energy fluctuations. At the core, helium fusion has begun in earnest. Unlike the smooth, steady hydrogen fusion of earlier life, helium fusion is episodic, irregular, and capable of creating layers of alternating nuclear burning, a hydrogen burning shell surrounding a helium burning shell, both wrapped around the contracting carbon-oxygen core. The interaction of these layers is complex, producing bursts of energy that ripple outward, heating the star's outer atmosphere and driving the dramatic pulsations that we observe from Earth. This layer structure is a hallmark of stars in the asymptotic giant branch, the final evolutionary stage of low to intermediate mass stars like Mira.
The red giant phase is also a period of significant chemical transformation. As helium and hydrogen fuse in these shells, heavier elements such as carbon, oxygen, and even nitrogen are created. Convection within Mira's massive envelope dredges up some of these fusion products to the surface, a process known as dredge-up. Over time, these elements will be expelled into space, seeding the interstellar medium and contributing to the formation of new stars, planets, and eventually, life itself. Mira is, in essence, already acting as a cosmic gardener, enriching its surroundings while nearing its own death. Red giants are also defined by their instability. Mira's enormous outer layers are not gravitationally secure. They are sensitive to pressure waves and shock fronts generated by the pulsations. As the outer layers expand and cool, dust and molecules form, making the atmosphere more opaque and exacerbating the pulsation cycle. This instability makes red giants like Mira prone to losing mass at remarkable rates, sometimes thousands of times greater than what the Sun sheds through its relatively gentle solar wind. Over tens of thousands of years,
Mira will eject a significant fraction of its mass, leaving behind only its dense carbon-oxygen core. The color of a red giant, deep red to orange, is a visible testament to its cooler surface temperature, generally around 3000 Kelvin, much cooler than the Sun's 5800 Kelvin. This cooler temperature, combined with the star's immense size, gives it a soft, glowing presence in the night sky, strikingly different from the small, pinprick white or blue lights of younger, hotter stars. Mira's red color is a visual representation of its advanced age, a sign that the once steady fusion furnace of its core has slowed and transformed into a complex, unstable engine. Being a red giant is both a magnificent and precarious state. Mira is massive enough that the internal forces of fusion still keep it luminous, but the outer layers are so bloated and loosely held that each pulsation threatens to peel away material into space. Its life at this stage is a balancing act, a constant tug-of-war between gravitational collapse and thermal expansion. This is why Mira's pulsations are not minor, they are immense, driving the star's outer atmosphere outward and creating the enormous stellar winds that eventually form its extended tail of gas and dust. The red giant phase also serves as a cosmic preview of our own sun's distant future. In roughly 5 billion years, our sun will swell into a red giant, shedding its outer layers in a manner similar to Mira, perhaps even engulfing the inner planets. Mira gives us a living laboratory to study the late stages of stellar evolution in real time, allowing astronomers to observe processes that will one day shape our own solar system. The changes in luminosity, the expansion of the outer layers, and the production of heavy elements all illustrate the intricate physics that govern a star's final acts. In Mira's red giant phase, time is both fleeting and expansive. From a human perspective, centuries of pulsation seem endless, but in cosmic terms, this phase lasts only a fraction of the star's total life, a brief spectacular swan song. Each pulse, each ejection of gas and dust, is a step toward transformation, toward a future white dwarf core surrounded by a glowing shell of expelled material. Yet even in this dying stage, Mira is intensely vibrant. Its energy output is tremendous, its pulsations are dynamic, and its influence on the surrounding interstellar medium profound. Mira as a red giant exemplifies the grandeur and fragility of stars at the end of their life. Its bloated envelope, unstable outer layers, and layered fusion shells make it a cosmic paradox. Enormous yet tenuous, bright yet unstable, dying yet dynamically alive. The red giant stage is not a quiet decline, but a period of intense activity, shaping the star's fate and enriching the galaxy with the elements necessary for future generations of stars and planets. Mira's life as a red giant is both a dramatic display of physics in action and a poignant reminder of the impermanence and cyclical nature of all cosmic phenomena.
Mira's story is not just one of a solitary star in decline. It is also the tale of an intimate celestial partnership. Orbiting in tandem with the pulsating red giant is its lesser-known but equally fascinating companion, Mira B, a dense and compact white dwarf. This companion transforms Mira's life and legacy from a solitary narrative of stellar aging into a dramatic example of how stars interact, exchange matter, and influence each other in ways both subtle and extraordinary. Mira B is significantly smaller and hotter than Mira A, the red giant, where Mira A is enormous with an extended, tenuous envelope of gas hundreds of times the sun's radius. Mira B is compact, roughly the size of Earth, but with a mass comparable to the sun. As a white dwarf, Mira B represents the endpoint of a star that has already exhausted its own nuclear fuel and shed its outer layers, leaving behind a dense, degenerate core composed primarily of carbon and oxygen. It no longer undergoes fusion. Instead, it slowly cools over billions of years, radiating residual heat as it drifts through space. Yet, despite its small size, Mira B exerts a powerful influence on its larger companion. Mira A's bloated outer layers are loosely held by gravity, making them highly susceptible to disruption. Some of this material, blown outward by the red giant's pulsations and stellar winds, drifts into the gravitational field of Mira B.
This process, known as accretion, allows the white dwarf to pull in gas and dust from its partner, forming a complex interaction between the two stars. Over time, streams of material from Mira A spiral toward Mira B, creating an accretion disk, a flattened, rotating ring of gas that swirls around the white dwarf before gradually falling onto its surface. This interaction gives the Mira system an almost theatrical quality. Mira A, the dying giant, sheds its outer layers into the void, while Mira B, the compact white dwarf, greedily captures some of this material, feeding on the remnants of its partner's life. The two stars are locked in a gravitational dance, orbiting each other at a distance of roughly 70 astronomical units, a span more than twice the distance between the Sun and Pluto. Their orbital period is estimated to be around 400 years, meaning that while the pulsation cycle of Mira A dominates short-term observations, the motion of the binary system unfolds over centuries. The presence of Mira B has important consequences for the evolution of the system. As Mira A continues to lose mass, the gravitational relationship between the two stars changes. The orbit may widen slightly, and the flow of material can intensify or decrease depending on the rate at which Mira A expels gas. Astronomers studying the system with advanced instruments such as the Hubble Space Telescope and the Atacama Large Millimeter Submillimeter Array, ALMA, have captured stunning images showing Mira B surrounded by streams of matter drawn from Mira A, highlighting the dynamic and ongoing interaction between the two stars. This relationship also has broader astrophysical significance. White dwarfs in binary systems are known to produce spectacular phenomena under certain conditions. If Mira B were to accumulate enough material, it could ignite surface hydrogen in a thermonuclear flare known as a nova, dramatically increasing in brightness for a short period. While there is no current evidence that Mira B is on the verge of such an event, the potential demonstrates how intimately binary systems can influence stellar evolution. The red giant's mass loss feeds the white dwarf, altering both stars' fates in subtle yet profound ways. From a visual standpoint, Mira's binary nature adds layers of complexity to what astronomers observe. When seen through sophisticated imaging, the star does not appear as a single point of light, but as two distinct sources, sometimes enveloped in shared gas and dust. The interaction between Mira A's stellar wind and Mira B's gravity creates fascinating structures in the surrounding medium, including filaments, arcs, and spirals of matter, all shaped by the orbital dance of the two stars. This makes Mira not only a pulsating variable star, but also a laboratory for understanding mass transfer in binary systems, which has implications for phenomena as varied as supernovae, planetary nebula, and the formation of compact objects. Mira B also provides a counterpoint to Mira A's life story. Whereas Mira A is large, luminous, and nearing death, the white dwarf is small, dense, and effectively immortal on human timescales, slowly cooling over billions of years, radiating residual heat as it drifts through space. Together, the two stars illustrate the duality of stellar evolution. One star nearing the end of its life through active pulsation and mass loss, the other a remnant of its own past, quietly consuming the material cast off by its partner. In essence, Mira A is the provider, and Mira B is the silent recipient, locked in an interstellar relationship that highlights the interconnectedness of cosmic processes. Observations of Mira and its companion have yielded fascinating insights into the mechanics of binary star interactions. The streams of material from Mira A to Mira B are often traced using ultraviolet and infrared imaging, revealing details invisible in optical light. These studies have shown that the mass loss from Mira A is not uniform, but occurs in clumps and filaments, likely influenced by the pulsation cycle and the gravitational influence of the white dwarf. The result is a dynamic and evolving system that can teach astronomers about everything from stellar winds to angular momentum transfer. Even beyond the physics, the concept of a star feeding its companion adds a poetic dimension to the Mira system. Here is a dying giant nearing the end of its life, still giving, shedding matter that will sustain another star, a small white dwarf for millennia. In this cosmic partnership, death and survival are entwined, showing that in the universe,
endings can also be beginnings, and that stars, even in their final acts, continue to influence and create. In the broader context of the galaxy, binary systems like Mira are more than curiosities. They are laboratories for understanding stellar evolution, mass transfer, and the creation of exotic phenomena. Mira B's presence amplifies the importance of Mira A's pulsations and mass loss, showing how one star's end-of-life processes can directly affect another. The binary system exemplifies the complex relationships between stars in the universe, illustrating that no star is truly isolated and that stellar evolution is often a collaborative story rather than a solitary journey. The interplay between Mira A and Mira B also hints at future developments. As Mira A continues to lose mass, its envelope will thin, and its pulsations may change in amplitude. Eventually, Mira will lose so much of its outer layers that Mira B may dominate the remaining gas dynamics, perhaps creating new phenomena detectable by astronomers in the coming centuries. For now, the two stars continue their centuries-long dance, one massive and pulsing, the other small and consuming, a reminder that even in the heavens, relationships shape destiny.
One of the most astonishing aspects of Mira, which elevates it from an already remarkable variable star to a true cosmic marvel, is its enormous tail, a structure stretching 13 light-years through space, a size so vast that it challenges our capacity to visualize it. This tail, trailing behind Mira like a comet's, is composed of gas and dust expelled by the star over thousands of years, forming a dynamic and evolving record of its interaction with the surrounding interstellar medium. The discovery of this tail has not only revealed the dramatic consequences of Mira's pulsations in mass loss, but has also provided a unique window into how stars shape their environments as they age. Mira's tail was first revealed in stunning detail thanks to the Galaxy Evolution Explorer satellite, which observed the star in ultraviolet light. The choice of ultraviolet was critical. While Mira's tail is invisible to the naked eye, in almost undetectable invisible light, ultraviolet imaging can capture the faint emission of excited hydrogen atoms and other ionized gases being swept away by the stellar wind. When astronomers examined GALEX's images, they were astonished to see a continuous, elongated stream of material stretching millions of times the distance from the Sun to the Earth, an unprecedented phenomenon for a single star visible in such detail. This tail is created as a natural consequence of Mira's motion through the galaxy. Mira is not stationary. It is traveling at a speed of about 130 kilometers per second relative to the local interstellar medium. As the star moves, its strong stellar wind, composed of gas and dust driven off by pulsations and radiation pressure, collides with the surrounding material in space. The interaction produces a bow shock in the direction of motion, while material that escapes gravitationally trails behind, forming the elongated tail. The result is akin to a boat cutting through water. A turbulent wake stretches behind, a record of both the star's journey and its gradual shedding of matter. The tail's length, a staggering 13 light-years, implies that it is a historical record, a timeline of Mira's activity extending over tens of thousands of years. Each particle of gas or dust in the tail represents material ejected during a previous pulsation or mass loss event, creating a chronological archive that astronomers can study to reconstruct Mira's evolutionary past. By examining the density, composition, and motion of the tail, scientists gain insights into the rates at which Mira has been losing mass, how its pulsations influence the surrounding environment, and even the nature of the interstellar medium itself. The discovery of this tail also underscores the extraordinary scale at which stellar processes operate. Mira's physical radius, though enormous, hundreds of times the Sun's, is minute compared to the span of its tail. The tail stretches across an expanse more than 1,000 times the distance from the Sun to Pluto, and it remains detectable from Earth thanks to the continuous illumination and excitation of gas by both the star's radiation and interactions with the interstellar medium. It is a literal trail of stellar evolution,
marking the path of a star moving through the galaxy, leaving a tangible imprint on the cosmos. Structurally, the tail is far from uniform. Observations reveal clumps, knots, and filamentary structures embedded within the stream, suggesting that the material ejection is not constant but episodic, corresponding to Mira's pulsation cycle and irregularities in its mass loss processes. The tail's morphology is also influenced by magnetic fields, turbulence in the interstellar medium, and shocks caused by the relative motion between the star and surrounding gas. These dynamics make the tail a living laboratory, showing how even seemingly isolated stars can sculpt their galactic environments. Mira's tail is also a reminder of the star's ultimate fate. The materials streaming away will not remain bound to Mira indefinitely. Over tens of thousands of years, it will disperse into the interstellar medium, enriching it with elements synthesized in the star's core: carbon, oxygen, nitrogen, and heavier elements. These are the very building blocks of future stars, planets, and perhaps life itself. In this sense, the tail is a cosmic testament to the regenerative cycles of the universe. Mira's death throes today will become the raw material for future stellar generations tomorrow. The tail's comet-like appearance has also captured the imagination of astronomers and the public alike. It is a rare instance where a star exhibits a visible wake over such a vast scale, blending the dynamics of stellar winds with galactic motion. Unlike a comet in the solar system, which is illuminated primarily by sunlight, Mira's tail is a product of both energetic processes intrinsic to the star and the physical impact of moving through the galactic medium, making it a hybrid of personal stellar activity and environmental interaction. The discovery of Mira's tail emphasizes the importance of multi-wavelength astronomy. Observing the star solely in optical light would reveal its pulsations and red giant properties, but the true extent of its influence, the vast stream of gas extending light years into space, required ultraviolet imaging to uncover. Later observations in infrared have further mapped the dust component, providing a comprehensive picture of how mass loss and stellar motion combine to shape the star's surroundings. These insights not only deepen our understanding of Mira itself, but also inform broader astrophysical models of how red giants contribute to the chemical evolution of galaxies. Ultimately, the tail of Mira is a visual and scientific symbol of the star's interaction with the universe around it. It demonstrates that stars are not isolated points of light, but active agents, leaving lasting imprints on the cosmic landscape. Every pulsation of Mira contributes to the tail. Every mass loss episode adds to its length, and every kilometer traveled through the galaxy extends the structure further. It is a living chronicle of stellar life, a 13 light-year-long testament to the star's dynamism, its motion, and its ongoing influence on the Milky Way. From an aesthetic perspective, the tail transforms Mira from a mere point of light into a cosmic storyteller. In its trailing stream of gas and dust, we can read a narrative of thousands of years of stellar evolution, of relentless pulsations and gradual decay, of movement and interaction. It is both a scientific treasure trove and a poetic reminder. Even in its death throes, Mira leaves a lasting legacy, tracing a path through the galaxy that will persist long after the star itself has faded into a white dwarf. The tail thus bridges scales in an extraordinary way. It links the intimate, almost human-scale observation of changing brightness over 332 days with the vast sweep of galactic motion spanning tens of thousands of years and light-years of space. By studying the tail, astronomers can measure Mira's velocity, track the rate of mass loss, and understand how a single star can influence a volume of space far larger than its own dimensions. It transforms the concept of a star from a simple glowing sphere into an agent of cosmic change, one whose influence extends across the galaxy. In this way, Mira's tail is more than a scientific curiosity. It is a statement of the star's presence, its history, and its legacy. It visualizes the passage of time in a way that the pulsation alone cannot,
creating a bridge between the fleeting scale of human observation and the vast timescales of stellar evolution. Mira is not merely a dying star. It is a moving, evolving force, leaving behind a luminous, ghostly trail that maps its journey through the cosmos, like the wake of a celestial voyager traversing the sea of the Milky Way. The discovery of Mira's tail marked only the beginning of understanding its true complexity. To truly appreciate the star's ongoing transformation and mass loss, astronomers needed to look beyond visible light. While the naked eye, or traditional optical telescopes, reveal Mira's pulsations and red giant glow, the ultraviolet and infrared spectra unveil a hidden universe surrounding the star, an environment in which gas and dust flow outward, interact with interstellar space, and trace the star's history in remarkable detail. Observations in these wavelengths revealed aspects of Mira that were previously invisible, transforming it from a pulsating red dot into a dynamic, evolving cosmic system. In the early 2000s, the Galaxy Evolution Explorer, or GALEX telescope, designed specifically to observe the universe in ultraviolet light, turned its sensitive instruments toward Mira. What it revealed stunned astronomers. Stretching 13 light-years behind the star was a glowing tail of material that had gone completely undetected in optical wavelengths. This tail, like a cometary wake, is composed primarily of hydrogen gas, heated and ionized as it interacts with the surrounding interstellar medium. The ultraviolet emission highlights areas of higher energy, where hydrogen atoms have been excited by shocks and radiation, making them visible only in this portion of the electromagnetic spectrum. The ultraviolet imaging allows scientists to measure the rate at which Mira is losing mass. Estimates suggest that Mira sheds material at a rate of roughly 10 to the -7th solar masses per year, an immense outflow compared to the Sun's comparatively gentle solar wind. Over thousands of years, this mass loss accumulates, forming an extensive envelope of gas and dust that contributes not only to the tail, but also to the broader interstellar medium. Each pulse of the star, each expansion and contraction of its outer layers, drives streams of gas into space, a process now vividly traced in the ultraviolet. Ultraviolet imaging also revealed the complex structure of the tail. It is not uniform. Instead, it contains clumps, filaments, and regions of varying density, evidence of turbulence in Mira's wind and its interaction with the interstellar medium. As the star moves through space at roughly 130 kilometers per second, it creates a bow shock at the leading edge, compressing gas in front of it, while leaving behind a trail of material that continues to glow in UV light long after it has left the star. This provides a sort of fossil record of the star's mass loss history, a visual timeline stretching back tens of thousands of years. Infrared observations, particularly those made by instruments like the Spitzer Space Telescope and the Infrared Astronomical Satellite, IRIS, complement the UV data by revealing the dust component of Mira's outflow. While the ultraviolet highlights hot, ionized gas, infrared imaging detects cooler dust grains that condense in the extended envelope as the star sheds mass. These grains absorb the star's light and re-emit it as heat in the infrared spectrum. Observations show that Mira is surrounded by a thick, clumpy envelope of dust, providing insight into how red giants contribute raw materials, carbon, oxygen, silicon, and heavier elements back into the interstellar medium. Together, the UV and infrared observations paint a comprehensive picture. Mira is losing mass at a staggering rate, creating an extensive multi-component tail of gas and dust. The ultraviolet reveals the energetic, ionized hydrogen streaming behind the star, while the infrared reveals the cold, dense dust expelled by the star's pulsations. These revelations transformed Mira from a well-known variable star into a living laboratory of stellar evolution, illustrating directly how dying stars recycle material into the galaxy. The tail's ultraviolet glow also allowed astronomers to measure the velocity and dynamics of the outflow.
GALEX images indicated that the material in the tail is moving at hundreds of kilometers per second relative to the surrounding medium, forming a wake shaped by the interaction between Mira's wind and the interstellar environment. These measurements help quantify the energy involved in the star's mass loss process and confirm that Mira is actively enriching its surroundings on a galactic scale. Moreover, the UV and infrared observations shed light on Mira's interaction with its companion, Mira B. Some of the material in the tail is gravitationally influenced by the white dwarf, creating arcs and spirals in the gas that reflect the binary dynamics. The combination of high-resolution infrared and ultraviolet imaging has allowed scientists to separate these structures and analyze the contributions of both the pulsating red giant and the gravitational influence of its companion. This synergy of observations provides one of the clearest examples of how binary systems can shape stellar mass loss. The discovery of Mira's tail in the ultraviolet also emphasized the importance of multi-wavelength astronomy in studying evolved stars. While objective observations reveal the star itself, ultraviolet imaging reveals the energetic hydrogen that traces stellar winds and shocks, and infrared imaging shows the dust grains that are expelled. Only by combining these wavelengths can astronomers reconstruct the full three-dimensional structure of the outflow, understand its composition, and measure the true scale of mass loss. In effect, these observations have turned Mira into a case study for understanding the late stages of stellar evolution and the way stars seed the galaxy with material for future generations. Beyond its scientific significance, the ultraviolet and infrared revelations make Mira a profoundly visual and poetic object. To the unaided eye, it is a flickering red star in the night sky, changing brightness over months. But with ultraviolet and infrared telescopes, it becomes a cosmic phoenix, shedding its life into space, leaving behind an intricate glowing trail, a record of thousands of years of stellar activity, any promise of renewal. Every photon detected in the ultraviolet or infrared carries information about energy, motion, and chemical composition, turning what appears to be a simple red star into a dynamic, interactive participant in the galactic ecosystem. The observations also raise broader implications for astrophysics. Mira's ultraviolet and infrared tail provides a template for understanding how other red giants interact with their environment, how mass loss contributes to the chemical evolution of galaxies, and how binary companions affect stellar winds. It underscores that the universe is not static, but constantly shaped by the life cycles of its stars. Mira is not only an individual phenomenon, but also a representative of the class of asymptotic giant branch stars, whose cumulative mass loss over millions of years plays a vital role in galactic ecology. In essence, the ultraviolet and infrared revelations have transformed our perception of Mira from a simple, pulsating variable star into a dynamic, interacting, and evolving system, leaving a clear, measurable imprint on its surroundings. They allow us to trace the flow of matter from the star into the galaxy, to visualize energy and material on enormous scales, and to appreciate the duality of creation and destruction inherent in stellar evolution. Mira is, in these wavelengths, not just a star but a cosmic storyteller, a red giant whose last acts leave both a physical and an observational legacy for the universe to read. Mira's story becomes even more remarkable when one considers not just the star itself, but its motion through the galaxy. While most stars appear fixed in the sky, slowly shifting over millennia due to the grand rotations of the Milky Way, Mira is a star on the move, racing through space at an astonishing 130 kilometers per second. To put that into perspective, this is more than 460,000 kilometers per hour, fast enough to circle the Earth's equator more than 11 times in a single hour. Mira's rapid motion is responsible for some of the most striking features of its environment, including a spectacular wake of gas and dust trailing behind it and the bow shock that leads its path like the prow of a galactic ship cutting through the interstellar medium. Mira's speed and trajectory give astronomers a unique opportunity to study how stars interact dynamically with their surroundings. As it moves, the stellar wind it generates, a continuous outflow of gas and dust driven by its pulsations and outer layer instability, collides with the interstellar medium. This interaction produces a bow shock, a compressed, arc-shaped region of gas and dust forming in the direction of motion. Ahead of Mira, the bow shock acts like the bow wave of a ship moving through water, compressing and heating material as it flows around the star. Behind the star, the expelled material forms the elongated tail, a 13 light-year-long trail visible in ultraviolet light thanks to GALEX. The shape and extent of Mira's tail are directly influenced by this high-speed motion. The star is effectively plowing through the galaxy, and its movement stretches the gas and dust into a long, thin stream. Each particle in the tail carries information about when it was ejected, how it interacted with Mira's stellar wind, and how the relative motion of the star and the surrounding medium has shaped its path. In this sense, the tail is not only a record of Mira's mass loss, but also a map of its journey through the Milky Way over tens of thousands of years. Astronomers can trace the motion and velocity of the tail to reconstruct Mira's trajectory and to study how stars moving through the galaxy stir the interstellar medium. Mira's aft motion is unusual, but not unique. Stars that travel at high velocities relative to their neighbors are often called runaway stars, sometimes ejected from dense star clusters or influenced by gravitational interactions with other stars or remnants such as black holes. While the exact reason for Mira's high velocity is still a matter of study, its speed, combined with its significant mass loss, ensures that the surrounding interstellar medium is constantly being reshaped. In effect, Mira is a moving workshop, sculpting the gas and dust around it as it speeds through space. The dynamics of Mira's journey also affect the distribution of the material it sheds. As the red giant pulsates and expels gas and dust, the star's motion causes this material to accumulate more densely in the trailing tail than in front. The bow shock ahead of Mira forms a high-pressure region where incoming interstellar gas is compressed, while the tail behind stretches out, forming filaments and clumps shaped by turbulence, shocks, and instabilities in the flow. The combination of high-speed motion and episodic mass loss creates a complex, three-dimensional structure that astronomers continue to map with both ultraviolet and infrared telescopes. The velocity of Mira also highlights the scale of the processes involved. Over its lifetime in the red giant phase, Mira has moved thousands of light-years relative to the local interstellar medium, leaving behind an extensive trail of gas and dust. This material, eventually incorporated into future generations of stars and planets, serves as a reminder that even as the star approaches the end of its life, its influence is far-reaching. Mira's journey shows that stars are not isolated points in space. Their paths can stir the medium around them, distribute elements, and shape the galactic environment on scales unimaginable in human terms. From an observational perspective, Mira's motion is measurable. Proper motion studies, using both historical astrometric data and modern high-precision measurements from instruments like Hubble and Gaia, allow astronomers to calculate both its speed and its direction across the sky. This provides insights not only into Mira itself, but also into the dynamics of the Milky Way, including how stars move in the galactic disk and how they interact with the surrounding interstellar medium. Mira, in effect, becomes a moving laboratory for understanding stellar motion and feedback processes on a galactic scale. Mira's journey is also poetic in its implications. As it races through the galaxy, leaving behind a glowing trail of its former self, it serves as a visible record of cosmic passage and transformation. Each pulsation of the star ejects gas and dust that is then swept along by the star's motion, creating a layered history of energy, matter, and time stretching across light years. The star becomes both a participant in and a chronicler of its own journey through the Milky Way. The interaction of Mira's motion with its mass loss has wider astrophysical significance. Stars like Mira, moving at high speeds and losing mass, contribute to the mixing of the interstellar medium, enriching it with elements synthesized during stellar evolution. This process ensures that heavy elements like carbon, oxygen, and nitrogen are spread far beyond the immediate vicinity of the star, making these critical building blocks available for future star systems, planets, and, eventually, life. Mira's journey is thus a story not only of motion, but of cosmic recycling on a galactic scale.
In essence, Mira's motion transforms a star from a static object in the sky into a dynamic agent of galactic change. Its high velocity, combined with the pulsations and mass loss of its red giant phase, creates an extraordinary visual and physical phenomenon. A comet-like tail, bow shock, and interstellar wake spanning light years. Mira's journey across the Milky Way is a reminder that stars are not fixed, unchanging points of light, but active, moving participants in the evolution of the galaxy, each one leaving behind a signature of energy, matter, and motion. By studying Mira's trajectory and its effects on the surrounding gas and dust, astronomers gain invaluable insight into the life cycle of stars, the behavior of stellar winds, and the processes that distribute heavy elements throughout the galaxy. Mira's motion turns the night sky into a dynamic canvas, where stars are not only shining but also moving, sculpting, and leaving behind trails that tell the stories of their lives and their journeys through the cosmos. Mira provides a vivid, tangible example of the life cycle of stars, illustrating the processes that govern stellar evolution from birth to death. By examining Mira's journey from a stable main sequence star to a bloated, pulsating red giant, and ultimately toward the formation of a white dwarf, astronomers have been able to witness stellar aging in a way that brings theoretical models to life. Mira is essentially a textbook for understanding how stars like our Sun are born, live, and die, offering a bridge between abstract physics and observable phenomena. Stars begin their lives within molecular clouds, immense, cold regions of gas and dust that serve as stellar nurseries. Gravity acts on clumps within these clouds, pulling material together until the density and temperature in the core become sufficient to ignite nuclear fusion. Mira, billions of years ago, emerged from one such collapse, starting its life as a main sequence star fusing hydrogen into helium at its core. This phase is the most stable period in a star's life. The outward pressure from fusion balances the inward pull of gravity, and the star shines with a steady light. Mira likely spent several billion years in this stable state, quietly converting hydrogen into helium and maintaining a relatively constant size, temperature, and luminosity. However, no star remains in this balanced state forever. As hydrogen fuel in the core is exhausted, the delicate equilibrium between radiation pressure and gravity begins to collapse. For Mira, this led to the onset of the red giant phase, the first stage of visible stellar aging. The core contracts, heating up as hydrogen fusion continues in a surrounding shell. Meanwhile, the outer layers expand dramatically, cooling as they grow larger, giving the star its characteristic red color. Mira's radius now extends hundreds of times that of the Sun, and its luminosity increases even as the surface temperature decreases. The red giant phase is inherently unstable, as evidenced by Mira's dramatic pulsations. Energy produced in the helium and hydrogen-burning shells drives outward pressure waves, causing the star to expand and contract periodically. These pulsations produce the variations in brightness that make Mira a prototype for Mira-type variable stars. The star's life during this stage is marked by intense mass loss, with stellar winds expelling gas and dust into space. These processes serve as a critical link in the cosmic cycle. The material lost by Mira will eventually seed the interstellar medium, forming the raw ingredients for new stars, planets, and possibly even life. As Mira continues along the asymptotic giant branch, AGB, helium in the core fuses into carbon and oxygen. The star alternates between phases of energy production in helium-burning and hydrogen-burning shells, creating thermal pulses that amplify mass loss and instability. Mira is in this phase simultaneously living, dying, and reshaping the galaxy around it. Each pulsation sheds material, contributing to the enormous tail stretching over 13 light-years and enriching its surroundings with heavier elements. The star is essentially performing the final active work of its life, recycling matter into the cosmos. Eventually, Mira will reach the end of its life as a red giant. The outer layers, already tenuous and loosely bound, will be completely expelled, forming a planetary nebula, a glowing shell of gas surrounding the dying star. The core, composed of carbon and oxygen, will remain behind, unable to sustain further fusion.
This remnant is the white dwarf, a dense, Earth-sized object with a mass roughly equal to the Sun's. While no longer generating energy through fusion, the white dwarf will radiate residual heat slowly over billions of years, fading gradually into darkness. Mira itself will follow this path, leaving behind a quiet but enduring remnant of its former brilliance. Mira's journey illustrates several key aspects of stellar evolution. First, it shows the finite nature of fusion. Stars have a limited supply of fuel, and the exhaustion of core hydrogen marks the first major turning point in their life cycle. Second, it highlights the role of mass loss in shaping both the star's evolution and the interstellar environment. Mira's pulsations and winds exemplify how stars contribute materially to the galaxy, ensuring that the elements force in their cores become the building blocks of future generations of stars and planets. Third, Mira demonstrates the connection between a star's initial mass and its ultimate fate. Stars of roughly one solar mass, like Mira, end their lives as white dwarfs, while more massive stars undergo supernovas, leaving behind neutron stars or black holes.
The beauty of using Mira as a case study is that its processes are observable in real time, something rare in astrophysics. Many stellar phenomena are theorized based on indirect evidence, but Mira allows astronomers to witness its pulsations, mass loss streams, and tail formation directly. Over decades, centuries, and even millennia, scientists can track its evolution, measure its luminosity fluctuations, and observe the interplay between the red giant and its white dwarf companion. Mira thus bridges theory and observation, providing a concrete example of stellar aging. Mira's life cycle also serves as a cosmic mirror, offering a glimpse into the distant future of our Sun. In roughly 5 billion years, the Sun will exhaust its hydrogen fuel and begin expanding into a red giant, undergoing processes strikingly similar to those now observed in Mira. The Sun will pulsate, shed material, and eventually leave behind a white dwarf, surrounded by a planetary nebula composed of gas and dust from its outer layers. In this sense, Mira is not just a distant star. It is a living forecast of our own solar system's destiny, providing invaluable insights into what awaits the Sun and the inner planets, including Earth. Studying Mira also highlights the cyclical nature of matter in the universe. From hydrogen clouds to main sequence stars, red giants, planetary nebulae, and white dwarfs, the elements forged in stars like Mira are returned to space to form new generations of stars and planets. Mira is both an endpoint and the beginning. It is a dying star whose pulsations, mass loss, and tail ensure that its legacy will continue in the cosmos for eons. Its journey exemplifies the eternal cycle of stellar birth, evolution, and death, demonstrating how even as individual stars fade, their influence persists in shaping the galaxy. In summary, Mira's life and death illustrate the stages every medium-mass star undergoes: birth in a molecular cloud, stable fusion on the main sequence, expansion and pulsation as a red giant, mass loss through winds and thermal pulses, and eventual collapse to a white dwarf. Its current state provides astronomers with a live laboratory for understanding these processes, offering insights into stellar physics, galactic chemical enrichment, and the eventual fate of our own solar system. Mira is, in every sense, a stellar chronicle, encapsulating billions of years of evolution within its pulsations, tail, and binary interactions. A story of creation, transformation, and legacy written across the cosmos. Mira's current state as a pulsating red giant offers an extraordinary preview of the fate awaiting our own Sun. While the Sun seems steady and unchanging in the night sky, it too is slowly marching through time toward a dramatic transformation. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel at its core, marking the end of its long and stable main sequence life, a fate remarkably similar to what Mira has already experienced. By studying Mira, astronomers can gain an invaluable window into our solar future,
observing processes that will one day play out in our own cosmic neighborhood. The first stage of this transformation will mirror Mira's red giant expansion. As the sun's core runs out of hydrogen, it will contract under gravity while the outer layers swell outward. Eventually, the sun will expand to a radius that may engulf the inner planets, including Mercury and possibly Venus, turning the solar system's innermost region into a fiery, molten landscape. This expansion will be accompanied by cooling of the surface layers, giving the sun a deep reddish hue and dramatically increasing its luminosity. Like Mira, the sun will transition into the asymptotic giant branch, where helium burning in the core and hydrogen fusion in surrounding shells create an unstable, pulsating environment. During this phase, the sun's outer layers will become increasingly tenuous, and pulsations similar to Mira's 332-day cycle will drive stellar winds that expel vast amounts of material into space. This mass loss is a critical aspect of the red giant stage, both for Mira and for the sun, and it is responsible for returning heavy elements, carbon, oxygen, nitrogen, and others synthesized in the core, to the interstellar medium. In effect, just as Mira is now contributing to the future generation of stars and planets, the sun will enrich the galaxy with the raw materials necessary for life and new stellar systems. One particularly vivid lesson Mira provides is the scale and mechanics of these pulsations. Mira's rhythmic expansion and contraction show that a star's surface is far from static during this late stage of life. Shock waves propagate through the star's outer layers, causing the ejection of matter in streams and clumps. By observing how Mira sheds its mass, astronomers can model how the sun will behave, predicting not only the rate at which material will leave the star, but also the eventual formation of a planetary nebula, a glowing shell of gas and dust surrounding the dying core. The sun's planetary nebula will likely be smaller than Mira's tail in absolute terms, but the physical processes will be nearly identical.
Another striking connection lies in binary interactions. While the sun is currently a solitary star without a white dwarf companion like Mira B, the dynamics of mass loss and wind interaction remain relevant. Mira demonstrates how expelled material interacts with surrounding environments, including nearby stars, interstellar gas, and magnetic fields. In the sun's case, its winds will shape the local interstellar medium, potentially creating structures analogous to Mira's bow shock and extended tail, though on a smaller and less dramatic scale due to the sun's slower motion relative to the surrounding medium. Mira also provides a cautionary preview regarding habitability and planetary survival. The intense expansion of the red giant sun will heat the remaining planets, boil off atmospheres, and likely engulf the innermost orbits. Just as Mira's envelope dwarfs its earlier, more compact dimensions, the sun will become a giant in the sky, a reminder of the impermanence of planetary environments in the face of stellar evolution. Earth itself may be rendered uninhabitable long before the sun reaches its maximum size, emphasizing the dramatic transformations that accompany a star's aging. Eventually, as Mira will, the sun will shed its outer layers entirely, leaving behind a white dwarf, a dense, slowly cooling core roughly the size of Earth, but with a mass comparable to the sun. This remnant will shine faintly, no longer powered by fusion, but radiating residual heat for billions of years. By studying Mira's mass loss processes, pulsations, and eventual evolution into a white dwarf, astronomers can model the timeline and characteristics of our sun's final stages with far greater precision than would otherwise be possible. Mira's example also highlights the cosmic recycling role that the sun will eventually play. The material expelled during the red giant phase will mix with the interstellar medium, providing elements necessary for the formation of new stars, planets, and potentially life elsewhere in the galaxy. Mira's tail and pulsation-driven mass loss are a vivid demonstration of how individual stars contribute to the ongoing enrichment of the Milky Way. And by analogy, the sun's eventual contribution will follow the same principles. In addition to offering scientific insights, Mira gives a deeply poetic perspective on our sun's destiny.
The star that warms Earth today and sustains life will, in billions of years, swell into a red giant, pulse with irregular brilliance, shed material into space, and leave behind a compact white dwarf. The processes Mira undergoes now, the expansion, the pulsations, the formation of a tail, and the enrichment of the surrounding medium, are a preview of this inevitable transformation. By observing Mira, humanity is essentially watching a live rehearsal of the sun's future, billions of years ahead of schedule. The connection between Mira and the sun is therefore both practical and philosophical. Practically, astronomers can use Mira as a model to predict mass loss rates, pulsation behaviors, chemical yields, and the eventual formation of a planetary nebula. Philosophically, Mira reminds us of the transient yet transformative nature of stars. Even as they die, they continue to influence the universe, leaving behind matter, energy, and structure that will persist long after their fusion-driven hearts have cooled. Our sun, in this context, is not merely a solitary star, but a participant in the universal cycle of birth, evolution, and death, a cycle vividly illustrated by Mira's ongoing journey. Studying Mira also allows scientists to anticipate the timelines involved. The red giant phase for a star like the sun will last hundreds of millions of years, relatively brief compared to the multi-billion-year main sequence lifespan. Mira's pulsations, tail formation, and mass loss provide a measurable timeline, offering a glimpse into the tempo of stellar aging. By comparing Mira's current state with models of the sun's evolution, astronomers can estimate how quickly material will be shed, when pulsations will peak, and how long the white dwarf phase will persist. In essence, Mira is both a mirror and a guide. It reflects the ultimate fate of medium-sized stars like our sun, while also guiding astronomers in understanding the physics of late stellar evolution. Its pulsations, mass loss, tail, and binary interactions serve as vivid lessons in the forces that shape dying stars and their environments. Observing Mira allows humanity to witness in real time the processes that will one day transform our solar system, a reminder of the impermanence and dynamism of the cosmos and of our own sun's eventual transformation into a red giant. Mira's role in the cosmos extends far beyond its own pulsations, tail, and red giant splendor. It serves as a cosmic recycler, a stellar engine that transforms the elements forged in its core into material that will ultimately give birth to future stars, planets, and potentially life itself. Every pulse, every gust of stellar wind, and every gram of gas and dust expelled into space is part of a vast cycle in which dying stars seed the galaxy with the raw ingredients for new cosmic structures. Mira's shedding of gas is not just a byproduct of its aging, it is an active contribution to the ongoing evolution of the Milky Way. As Mira continues its red giant phase, its outer layers become increasingly tenuous, expanding and cooling under the combined forces of gravity, pressure from the fusion shells, and radiation. These layers are only weakly bound to the star, making them highly susceptible to the forces driving stellar winds. The result is a steady but powerful outflow of gas and dust, enriched with elements synthesized in the star's core over billions of years. This includes helium from hydrogen fusion, carbon and oxygen from helium fusion, and nitrogen from additional nuclear reactions. These heavier elements, collectively known as metals in astronomical terms, are the very substances that allow future generations of stars and planets to form and even make life possible. The mass loss from Mira is not a uniform or gentle process. It is punctuated by the star's pulsations, which periodically expand and contract its outer layers. During the expansion phase, cooler temperatures allow dust grains to condense from the ejected gas, forming solid particles that can survive long journeys through space. These grains are then carried away by the stellar wind, sometimes accelerated by radiation pressure, forming an extended envelope of gas and dust around the star. Over time, this material is spread across interstellar space, mixing with the surrounding medium and creating the raw material for the next generation of stars and planets. The tail of Mira, stretching 13 light-years behind the star, provides a dramatic visual example of this process. This tail is not merely a spectacular feature, it represents the physical evidence of cosmic recycling in action. Each particle in the tail, whether ionized gas visible in ultraviolet light or cooler dust detectable in the infrared, is a fragment of Mira itself, enriched with elements that were once trapped in the star's core. As the star continues to plow through the galaxy, this material disperses into the interstellar medium, gradually mixing with hydrogen clouds that will one day collapse to form new stars. Mira is in essence depositing the building blocks of future worlds along its path, leaving a legacy that will endure long after the star itself has faded into a white dwarf.
Mira's role as a cosmic recycler also illustrates a broader principle in stellar evolution. Stars are not isolated actors, but participants in a galactic ecosystem, exchanging mass and energy with the surrounding environment. When Mira ejects material, it contributes not only hydrogen and helium, but also heavier elements that were forged over billions of years of fusion. This enrichment increases the metallicity of the interstellar medium, making subsequent generations of stars more chemically complex. Planets that form around these stars are likely to contain heavier elements, including carbon, oxygen, silicon, and iron, the essential ingredients for rocky planets and, potentially, life. In this way, Mira's death throes directly shape the chemical and physical conditions of the Milky Way. The interaction of Mira's expelled material with the interstellar medium also creates shocks and turbulence, stirring and compressing surrounding gas clouds. These disturbances can act as catalysts for star formation, triggering the collapse of molecular clouds that otherwise might remain stable. The star's motion through the galaxy, coupled with its strong stellar winds, ensures that the enriched material is not confined to a single location, but is distributed along its path, increasing the likelihood that it will be incorporated into new stellar systems. Mira is, therefore, not just shedding matter, it is actively shaping the environment in which future stars and planets will emerge.
Observations in both the ultraviolet and infrared confirm that Mira is losing mass at an impressive rate. GALEX revealed the glowing tail of ionized hydrogen, while infrared telescopes like Spitzer have mapped the cooler dust grains. Together, these observations show that Mira's mass loss is a multi-component process, simultaneously ejecting gas and dust into space at velocities of hundreds of kilometers per second. This combination ensures that the material spreads over vast distances, gradually mixing with other stellar ejecta and the primordial gas of the Milky Way. Over tens of thousands of years, this process contributes a significant fraction of the interstellar medium's mass, demonstrating the star's essential role in galactic recycling. Mira's binary companion, Mira B, adds an additional dimension to this recycling process. Some of the injected material is captured by the white dwarf, forming an accretion disk and undergoing further interactions that can enrich and redistribute elements in localized regions. The gravitational interaction between the two stars shapes the outflow, creating spirals, arcs, and filaments that enhance the mixing of matter into the surrounding space. Mira's material is therefore not only distributed broadly along its tail, but also sculpted by the dynamics of the binary system, creating a rich and varied input into the galactic ecosystem. The importance of Mira as a cosmic recycler extends beyond the local environment. By studying how Mira ejects material, astronomers gain insight into how low to intermediate mass stars, the most common type in the galaxy, contribute to the chemical evolution of the Milky Way. Unlike massive stars that end in supernovae, these stars enrich the galaxy more gradually, continuously supplying gas and dust over hundreds of thousands of years. Mira is a vivid, ongoing example of this process, illustrating that even stars of relatively modest mass have a profound impact on the composition and evolution of the galaxy. On a philosophical level, Mira's recycling process is deeply symbolic. It demonstrates that death in the cosmos is not an end, but a transformation. As a star expels its outer layers, it spreads the seeds of creation throughout the galaxy, ensuring that its legacy continues in the next generation of stars, planets, and potentially life.
Mira is simultaneously a dying star and a progenitor of new beginnings, a living testament to the interconnectedness of cosmic processes and the cyclical nature of the universe. Ultimately, Mira's shedding of gas exemplifies the broader role of red giants in galactic ecology. These stars act as both endpoints and beginnings, processing primordial material into heavier elements through nuclear fusion and then redistributing that matter through pulsations, winds, and tails. In the grand story of the cosmos, Mira is both a contributor and a catalyst, enriching the galaxy with the ingredients necessary for future stars, planetary systems, and perhaps life. In this way, Mira embodies the profound interconnectedness of stellar evolution, demonstrating how the life and death of a single star reverberates across light years of space and time, shaping the future of the Milky Way. For amateur astronomers, Mira presents a rare opportunity to witness the dynamic life of a star unfolding in real time. Unlike most stars which shine with the constant brightness over human timescales, Mira's luminosity fluctuates dramatically, making it one of the few stars whose variability is easily observable without sophisticated equipment. Tracking Mira is not only a scientific pursuit, but also a profoundly satisfying experience, as observers can literally see the pulsations of a distant star and follow its cycle over months and years, connecting directly with processes happening hundreds of light years away.
Mira is located in the constellation Cetus, the sea monster, which occupies a portion of the sky along the celestial equator. This positioning makes Mira visible from both the northern and southern hemispheres for much of the year, though the optimal viewing season in the northern hemisphere is generally during autumn and winter months, when Cetus rises high in the evening sky. The star lies roughly midway between the constellations Pisces and Eridanus, and its precise coordinates are RA02H19 M20.8S, DEC -02 degrees, 58 minutes, 39 prime. For observers unfamiliar with detailed star charts, Mira can be found by locating the easily recognizable pattern of Cetus's body stars and identifying a reddish point of light that stands out during its maximum brightness. Mira's variability is dramatic enough that it can be observed with the naked eye at its peak. When at maximum brightness, Mira reaches around magnitude 2, making it easily visible even in moderately light-polluted urban areas. However, as it dims toward minimum, it drops to about magnitude 10, rendering it invisible to the naked eye and requiring at least a small telescope to detect. This change occurs over a roughly 332-day cycle, giving observers nearly a full year to witness the rise and fall of the star's luminosity. Because the cycle is predictable, dedicated observers can plan their observations to capture both the peak and the minimum, effectively documenting the pulsations. For those wishing to track Mira, binoculars or small telescopes are sufficient to observe changes in brightness during the dimmer phases. A key tip is to compare Mira with nearby stars of known magnitude. Using a method called visual photometry, observers estimate Mira's brightness by noting whether it appears brighter or dimmer than surrounding stars. Over months, repeated observations allow for the construction of a light curve, a graph of brightness versus time, which reveals not only the 332-day pulsation, but also subtler variations in amplitude that may occur from cycle to cycle. Many amateur astronomers contribute these observations to organizations like the American Association of Variable Star Observers, AAVSO, helping professional astronomers refine models of Mira-type stars. The experience of observing Mira is enhanced by understanding its color changes. At maximum brightness, Mira's surface temperature slightly increases, and it may appear more orange or reddish, while at minimum brightness, the star appears a deeper red. These subtle color shifts correspond to the expansion and contraction of the star's outer layers and provide an additional layer of observable data for those with telescopes capable of distinguishing color variations. Observers often remark on the star's ethereal glow, describing it as a living entity in the sky, pulsing in a rhythm that can be tracked night after night. Because Mira's period is slightly less than a year, observing over multiple cycles allows enthusiasts to notice long-term trends. Some cycles may reach slightly higher or lower peak magnitudes, or the duration between maxima may shift by a few days, due to irregularities in the pulsation. This variability adds depth to the observation experience, as it demonstrates that even stars can exhibit unpredictability, revealing the dynamic physics at work in their outer layers. Keeping a consistent log of observations, ideally with dates, time, and estimated brightness, can build a record that spans years and decades, providing both a personal archive and potentially valuable scientific data. In addition to naked eye and small telescope observations, photography and CCD imaging offer another way to study Mira. By taking images at regular intervals, amateur astronomers can digitally measure the star's brightness using comparison stars in the same frame. Modern software allows for precise measurements, enabling even casual observers to contribute to scientific research. Observing Mira in different filters, such as red or infrared, can also reveal more about the star's temperature changes and atmospheric dynamics. These techniques connect the visual experience to quantitative data, bridging the gap between aesthetic enjoyment and scientific contribution.
Mira's location near the celestial equator also means it rises and sets at predictable times, making it accessible for observing throughout the night during the peak months. Observers in the northern hemisphere may find it rising in the southeast in the early evening during autumn, and reaching its highest point in the sky around midnight. In the southern hemisphere, the star appears higher in the sky during spring and early summer months. Tracking its position in relation to constellations like Pisces, Aries, and Eridanus helps contextualize its motion and makes it easier to plan observations across the pulsation cycle. One of the joys of observing Mira is the connection across centuries of astronomical history. From David Fabricius first noticing its variability in 1596 to Johannes Hevelius naming it Mira in the 17th century, observers have been charting this star for over 400 years. Modern amateurs participating in the same practice are essentially continuing a centuries-long tradition, witnessing a phenomenon that has fascinated humanity for generations. This continuity provides both a scientific and a poetic resonance. By observing Mira, one participates in a dialogue with astronomers of the past and contributes to the collective understanding of stellar evolution. Finally, observing Mira is also an opportunity to understand its broader context in the galaxy. While watching the star change brightness over months, one can reflect on its enormous tail stretching across 13 light-years, its pulsating red giant envelope, and its high-speed journey through the Milky Way. Even a small telescope allows a glimpse into these larger processes by capturing the star at different points in its pulsation cycle. The act of tracking Mira from Earth transforms the observer into a participant in the cosmic cycle, directly engaging with phenomena that have been unfolding for tens of thousands of years. In conclusion, Mira is both an accessible target for amateur astronomers and a profound educational tool. By observing its pulsations, tracking its brightness, noting its color changes, and situating it within its galactic environment, observers gain first-hand experience of stellar evolution, mass loss, and the life cycle of stars. Whether using the naked eye, binoculars, small telescopes, or advanced imaging equipment, following Mira over months and years allows enthusiasts to witness the living, breathing dynamics of a distant star, connecting with both the science and poetry of the cosmos in a deeply personal and ongoing way. The discovery of Mira marked a profound turning point in astronomy, laying the groundwork for the modern understanding of stellar evolution, variability, and the dynamic nature of stars. Before Mira, stars were largely considered fixed, unchanging points of light in the night sky, their constancy taken as a given by generations of astronomers. The realization that a star could change its brightness, rhythmically and predictably, challenged centuries of assumptions and opened the door to a new field of scientific inquiry, the study of variable stars. In this sense, Mira's discovery was not merely about a single star. It was the first glimpse into the living, breathing nature of the cosmos. When David Fabricius first observed Mira's variability in 1596, he noticed something that had never been formally recorded: a star that appeared and disappeared from view over time. Fabricius was meticulous in his observations, recording the brightness changes over weeks and months, and his work hinted at underlying physical processes at play, though the physics of stars was not yet understood in the 16th century. This initial discovery was revolutionary because it undermined the long-held belief that the heavens were immutable. A star could change, and if one could, perhaps others could as well. Mira became the prototype for recognizing stellar variability as a genuine astrophysical phenomenon rather than an observational anomaly. The significance of Mira's discovery was amplified when Johannes Hevelius, in the 17th century, named the star Mira, meaning wonderful or astonishing. This recognition reflected both the human fascination with the star and its scientific importance. By the 18th and 19th centuries, astronomers began systematically observing Mira and other variable stars, documenting their periods and magnitudes. Mira's predictable pulsations, rising from magnitude 10 to magnitude 2 every 332 days, provided a measurable, repeatable phenomenon that could be studied with growing precision. This laid the foundation for the first classification schemes of variable stars, eventually leading to the identification of different types, including Mira variables, Cepheids, and eclipsing binaries. Mira's influence on astrophysics is particularly profound in its role as a prototype for Mira-type variable stars, a class of pulsating red giants characterized by long periods and large amplitude changes in brightness. Observations of these stars have allowed scientists to understand that variability is linked directly to internal processes, changes in temperature, pressure, and energy transport within the star's outer layers. Mira showed that stars are not static, but undergo cyclical expansions and contractions, converting internal nuclear processes into observable brightness changes. This concept, now fundamental to stellar astrophysics, was first concretely demonstrated by Mira and its subsequent observations over centuries. Moreover, Mira's discovery has broader implications for understanding stellar life cycles. Before studying variable stars, astronomers lacked a concrete method for tracking the stages of stellar evolution. Mira, as a red giant exhibiting pulsations and mass loss, provided direct evidence that stars undergo significant transformations after leaving the main sequence. Observing its dramatic changes and the shedding of matter revealed that stars do not simply burn steadily until they disappear. Instead, they evolve, pulsate, and interact with their environment. This insight laid the conceptual foundation for the field of stellar evolution, which later developed fully through the work of 20th century astronomers and astrophysicists. In addition, Mira's discovery inspired the systematic study of stellar variability as a tool for measuring astronomical distances and understanding galactic structures. While Mira itself is not a standard candle like Cepheid variables, its classification helped establish the principle that periodic variations in brightness could be linked to intrinsic stellar properties, such as mass, radius, and luminosity. Observations of Mira and its analogs ultimately led to methods for determining distances to stars and galaxies, shaping the tools astronomers use to map the cosmos. Mira's legacy also extends into the realm of multi-wavelength astrophysics. Observing its pulsations in visible light was only the beginning. Later studies in infrared, ultraviolet, and radio frequencies revealed additional layers of complexity. Mass loss, dust formation, binary interactions, and the enormous 13 light-year tail of ejected material. These studies, grounded in the initial recognition of Mira's variability, expanded astrophysics into a multidisciplinary endeavor, combining observations, theory, and modeling to understand how stars live, die, and contribute to the galactic ecosystem. Without the pioneering observation of Mira's changing brightness, the need to explore stars in different wavelengths might not have been as urgent or obvious. The impact of Mira's discovery is also evident in amateur and professional collaborations. Because its brightness variations are observable with modest equipment, Mira became a star around which citizen scientists could gather valuable data. Observations collected by dedicated amateurs over decades have enriched professional research, providing long-term light curves that help refine models of pulsation, mass loss, and stellar structure. This collaborative approach, tracing back to the earliest recognition of Mira's variability, remains a cornerstone of modern astronomy.
Furthermore, Mira has become a touchstone for astrophysical theory. By studying its pulsations, astronomers developed models of radiostellar oscillations,
linking observed brightness changes to physical expansions and contractions of the star's outer layers. These models now form the basis for understanding not only Mira-type variables, but also other classes of pulsating stars. The star's mass loss, observed as both a stellar wind and a trailing tail, has helped shape theories of late-stage stellar evolution, showing how stars contribute material to the interstellar medium and influence galactic chemical evolution. In essence, Mira's scientific legacy is profound because it shifted our understanding of stars from static lights in the sky to dynamic, evolving entities. The discovery of its variability challenged centuries of assumptions, inspired systematic study, and became the foundation for stellar astrophysics. From early visual observations to modern multi-wavelength studies, Mira has guided astronomers in understanding the cycles of birth, evolution, and death that govern all stars. It is a bridge between centuries of human curiosity and the sophisticated astrophysics of today. A single, wonderful star whose pulsations have echoed across time and space to illuminate the workings of the universe. Through Mira, humanity learned that stars are not eternal constants, but living systems, capable of change, interaction, and influence on their surroundings. Its discovery opened the door to measuring stellar masses, ages, and compositions, to modeling the life cycle of stars, and to exploring the fundamental processes that drive the evolution of galaxies. Mira is not only a historical milestone in astronomy, it is a continuing testament to the power of careful observation, curiosity, and the enduring quest to understand the universe. Mira continues to captivate astronomers not just as a historical curiosity, but as a laboratory for cutting-edge astrophysical research, with modern instruments providing unprecedented insights into its structure, dynamics, and evolution. Long after its discovery over 400 years ago, Mira remains at the forefront of observational astronomy, illustrating both the advances in technology and the enduring scientific value of variable stars. Today, telescopes like Hubble, ALMA, Atacama Large Millimeter Submillimeter Array, and GALEX, Galaxy Evolution Explorer, are probing Mira across the electromagnetic spectrum, each revealing different facets of the star's complex behavior. Hubble Space Telescope observations have been instrumental in resolving fine structures in Mira's circumstellar environment. Its high-resolution imaging allows astronomers to study the star's pulsating atmosphere, its companion Mira B, and the intricate patterns in the ejected gas and dust. One of Hubble's key contributions has been capturing the interaction between Mira A, the red giant, and Mira B, the white dwarf companion. The images reveal spiral structures and arcs in the material flowing from Mira A toward Mira B, shaped by gravitational interactions and the dynamics of the binary system. These observations help astrophysicists understand how mass transfer occurs in binary systems and how companion stars influence stellar wind patterns, creating a more complex and anisotropic outflow than would occur in a solitary red giant. ALMA, operating at millimeter and submillimeter wavelengths, provides another dimension by probing cold molecular gas and dust surrounding Mira. Unlike visible or ultraviolet light, which highlights hot ionized material, ALMA traces cooler, denser regions where dust grains condense and accumulate. These observations have allowed scientists to map the distribution of molecules like carbon monoxide, CO, in Mira's extended envelope, revealing how gas and dust are expelled and how they interact with the surrounding interstellar medium. ALMA has also been crucial in quantifying the mass loss rate of Mira, helping refine models of red giant evolution. By measuring molecular emission lines, astronomers can determine both the velocity and density of the outflowing material, giving precise insights into the mechanisms driving stellar winds. GALEX, which observes in the ultraviolet spectrum, continues to provide dramatic evidence of Mira's energetic interactions with its environment. Its imaging of the star's 13 light-year-long tail demonstrates not only the extent of the material being shed, but also the way it interacts with interstellar gas. The ultraviolet light highlights hydrogen atoms that have been ionized by shocks and high-energy radiation, tracing the movement of material along the tail and offering a dynamic view of the star's mass loss history. GALEX data have revealed knots, filaments, and variations in brightness along the tail, showing that Mira's outflow is turbulent and complex rather than uniform. These observations are critical for understanding how red giants distribute material on a galactic scale.
Modern research also focuses on the chemistry of Mira's expelled material.
Observations with ALMA and other radio facilities detect molecules like water, silicon monoxide, and other organic compounds forming in the stellar wind. These molecules, combined with dust grains, represent the building blocks for future planetary systems. By analyzing the chemical composition of the material leaving Mira, scientists can study the enrichment of the interstellar medium, tracing how elements synthesized in stars are recycled into subsequent generations of stars and planets. This research directly ties into the broader concept of stars as cosmic recyclers, showing in real time how dying stars contribute to the galactic ecosystem. Another active area of research involves pulsation-driven mass loss. Mira's 332-day brightness cycle is not just a visual phenomenon, it reflects deep physical processes within the star. Observations from Hubble and ground-based telescopes monitor the expansion and contraction of the outer layers, while spectroscopic studies measure how these pulsations accelerate material outward. These data are helping astronomers understand the mechanical processes behind stellar winds, including the role of shock waves generated during pulsation cycles. By linking the timing and amplitude of pulsations with observed mass loss rates, researchers can refine models of red giant evolution and predict how stars like Mira and the Sun will behave during their late stages. Mira's binary system also offers a unique testbed for accretion physics. Material stripped from Mira A can accumulate on Mira B, forming an accretion disk and occasionally producing energetic outbursts. Observations across multiple wavelengths, ultraviolet from GALEX, optical from Hubble, and millimeter from ALMA, reveal the complex interactions between the two stars. These studies help astronomers understand phenomena such as mass transfer, disk formation, and wind shaping, which are relevant not only for Mira but also for other binary systems, including those that might evolve into cataclysmic variables or Type A supernova progenitors. Time domain astronomy has become another key component of modern Mira research. Continuous monitoring with both professional and amateur telescopes allows for the construction of long-term light curves, capturing subtle variations in period, amplitude, and irregularities in pulsation. These data, combined with high-resolution imaging and spectroscopy, enable a multi-scale, multi-wavelength understanding of Mira's dynamic processes, from the microphysics of its atmosphere to the macrostructure of its tail and surrounding environment. In addition, computational modeling now complements observational data, using the high-resolution images and spectral information to simulate Mira's pulsations, mass loss mechanisms, dust formation, and interaction with Mira B. These models provide predictions that can be tested against ongoing observations, creating a feedback loop that continuously refines our understanding of red giant stars. For example, simulations of Mira's wind dynamics reproduce the spiral and filamentary structures observed in the Hubble and ALMA images, confirming theoretical predictions about how pulsations, radiation pressure, and binary interactions shape the outflow. Mira also serves as a benchmark for other Mira-type variable stars. By studying one of the closest and most accessible examples in such detail, astronomers can extrapolate findings to similar stars throughout the galaxy. This has implications for understanding the broader population of asymptotic giant branch stars, their contributions to galactic chemical evolution, and the diversity of mass loss behaviors across different stellar masses and metallicities. In summary, modern research on Mira is a multifaceted effort that integrates observations from Hubble, ALMA, GALEX, and other telescopes to probe its mass loss, dust formation, pulsation dynamics, and binary interactions. These studies reveal the star as a dynamic, interacting system, where the outer layers expand and contract, matter is expelled into space, dust grains condense, and a long tail of material traces the star's journey through the galaxy. Mira continues to teach astronomers about the late stages of stellar evolution, the physics of red giant pulsations, and the way stars recycle matter into the cosmos, making it not only a historically significant star, but also a living laboratory for modern astrophysics.
Mira, the star that has fascinated astronomers for more than 4 centuries, leaves behind a legacy that is both scientific and poetic, a bridge between observation, theory, and human imagination. Even as a dying red giant, Mira pulses with life, a rhythmic heartbeat visible across hundreds of light years, reminding us that stars are not static points of light, but dynamic, evolving entities with stories to tell. Its oscillations, brightening and dimming in a roughly 332-day cycle, are like a cosmic metronome, marking the passage of time on a scale far beyond human experience, while simultaneously making the universe tangible and relatable. There is a profound beauty in observing a star that is in the final stages of its life, yet continues to influence its surroundings in multiple ways. Mira's pulsations, mass loss, and the spectacular 13 light-year tail of gas and dust are not just physical phenomena. They are visible expressions of the continuity of matter in the universe. The very material being shed from Mira will one day participate in the formation of new stars and planets, meaning that this ancient star is both an end and the beginning. It is a reminder that the cosmos is a living, interconnected system, where life, death, and rebirth are universal processes playing out on a grand scale. On a personal level, Mira connects observers across time. From David Fabricius's first recognition of its variability in 1596, to amateur astronomers today tracking its pulsations in their backyards, the star has inspired generations to look upward with curiosity and wonder. Each observation, whether by telescope or with the naked eye at its brightest, is a participation in a centuries-long dialogue between humanity and the cosmos. Mira serves as a poetic anchor in the night sky, a tangible reminder that even distant stars have rhythms, personalities, and life cycles we can perceive and study. The scientific lessons of Mira are equally profound. As the prototype for Mira-type variable stars, it taught astronomers that stars are not eternal and unchanging, but instead evolve over millions or billions of years, undergoing predictable yet complex changes. Its pulsations illuminate the mechanics of red giants. Its tail demonstrates the interaction of stellar winds with the interstellar medium, and its mass loss shows how stars act as cosmic recyclers, enriching the galaxy with heavy elements. Through Mira, science has gained insights into the late stages of stellar evolution, the life cycle of medium-mass stars, and even the distant future of our own sun. It is a star that literally embodies both the rhythm and the process of cosmic evolution. Mira's existence also highlights the interplay between observation and theory in astronomy. Its discovery challenged the centuries-old assumption of fixed stars, prompting the development of variable star research and laying the foundation for modern stellar astrophysics. Modern instruments like Hubble, ALMA, and GALEX continue to probe its complexities, revealing intricate details about mass loss, binary interactions, and dust formation. In this way, Mira serves as a living laboratory, a single star whose study continues to refine our understanding of stellar physics, galactic ecology, and the broader universe. Beyond the science, Mira is a reminder of the poetic and philosophical dimensions of astronomy. Its pulsations, brightness, variations, and long trailing tail evoke imagery of cosmic life cycles, movement, and transformation. Mira's story connects the human experience to the vast scales of space and time. A star born billions of years ago, now in its twilight, continues to leave a visible imprint across light years, a tangible record of its existence for anyone who chooses to observe it. The star embodies the duality of death and continuity, illustrating that even in the final stages of life, energy, matter, and influence persist. Moreover, Mira's influence extends metaphorically to the broader universe. It demonstrates how individual elements, stars, planets, gas, and dust are interconnected within galactic systems. The material expelled by Mira contributes to future generations of stars and planetary systems, illustrating a profound cosmic recycling process. Its life and death remind us that existence is a continuum, and even as individual objects fade, they continue to shape the cosmos in enduring ways. Mira is, in a sense, immortal, not in its physical structure, but in its enduring contribution to the galaxy and the scientific and cultural understanding of the universe.
For those who look up at the night sky, Mira serves as both a scientific object and a source of wonder. Watching it brighten and dim over the course of a year connects observers to the rhythms of the universe in an immediate and personal way. The star's changes are subtle yet dramatic, slow yet perceptible, making them a poetic counterpoint to the otherwise seemingly unchanging stars around it. It is a reminder that the universe is dynamic, alive with processes unfolding over timescales that dwarf human experience, yet which we can still witness with curiosity, patience, and attention. Ultimately, Mira is a symbol of continuity, resilience, and transformation. Even as it nears the end of its life, it continues to pulse, shed material, and influence its surroundings. Its tail stretches light years behind it, a luminous testament to its journey, and the elements it disperses will become the foundation for new stars and planets. Through observation, study, and reflection, Mira enriches our understanding of both the physical universe and our place within it. Its pulses are a cosmic heartbeat, its variability a narrative of life and death, and its material contributions a promise of new beginnings. In closing, Mira exemplifies the awe-inspiring beauty of astronomy, where the scientific and the poetic coexist. It is a star that refuses to fade quietly into darkness, instead illuminating the sky and our understanding of the universe with each rhythmic pulse. Its existence encourages us to see the cosmos as dynamic and interconnected, a vast arena of life cycles and transformations that continue to unfold over incomprehensible spans of time. Mira is truly the wonderful, not only for its physical phenomena, but also for the ways it inspires observation, reflection, and wonder, a living testament to the enduring power of stars to teach, to captivate, and to illuminate. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.